than normal. Chirality. All right, and actually, let's take some. This chapter in particular is where I found out, as a student, I really needed my model kits to help me out. Down. One more. All right, so chapter 5 is going to be about chirality. So what the heck does that mean? So we had said last time we had introduced this concept of stereoisomers. And we said that for our cyclic alkanes, we had these two different stereoisomers. What do we label those? So for the ring, right, there were two molecules that were, they had the same connectivity of atoms, but they were oriented differently in space. So when these two groups were on the same side of the ring, we called those the cis isomer, and when they were pointed on opposite sides, we had the trans isomer, right? So this was this type of stereochemistry that we learned about that was specific to cyclic alkanes. All right? Now, we said alkanes by themselves, regular alkanes, they don't have this same sort of cis and trans phenomenon because you can rotate around those single bonds, right? But what we're going to see is that our alkanes have another type of stereoisomer called R or S, and this indicates the chirality of that molecule. Okay? All right, so we're going to learn some terminology here. A pair of enantiomers. These are molecules that are mirror images of one another. Okay? So if we took, for example, this molecule here, and put a chlorine on this wedge here. Okay? We want to be able to draw its enantiomer, the mirror image of this molecule here. All right? What we're going to do is we're going to put our mirror here, right down the middle. Oh, sorry, will you pop that lock? My bad. Okay. And now we have to draw its mirror image. And much like when we were doing Newman projections, we got to pay attention to which way our carbons are pointed. Right? So if I'm going to draw its mirror image, now I need to go down first. Okay. And my mirror image is going to have my chlorine right there. So this would be a pair. There's underneath it. Over this one. In here. Okay, so these two molecules are distinct. They are not identical molecules. They are actually two different molecules. They are a pair of enantiomers. They are mirror images of one another. All right? They will have very, very similar properties, very similar boiling points and reactivities, but nonetheless, these are not the same thing. These are a pair of distinct molecules here. Okay? So this is this new type of stereoisomer where you have your mirror image of one another. This is often the analogy that's used is our hands. We have these two hands. They look very, very similar, but they are not superimposable on one another. They are mirror images of one another. Okay? Molecules have this same sort of handedness, or can have this same sort of handedness, where they have a mirror image that is not identical. Some molecules, their mirror image is identical, right? If I, in fact, just took the butane part without that chlorine on there, took its mirror image, all right, these are the same thing. I haven't actually made a new molecule here. All right? You're just going to trust me for right now that these are different, and we're going to learn a sort of set of rules to figure out whether molecules have enantiomers or not. Okay? So this would not, but this would be a pair of enantiomers. Okay? And this, we're going to learn sort of two different ways to be able to spot whether a molecule is enantiomers or whether to draw them. This is what we're going to call the mirror image method. All right, so let's build one of these real quick. We need 4 carbons. All right, we can leave off our hydrogens except for on that one carbon with the chlorine on it. All right, so on that one carbon, make sure to put in your 4 bonds. Got your chlorine on there too, excellent. Okay, take a second and see which one you built here. Did you build the one on the left or the one on the right? It depends on which way your carbons or your chlorines pointing out at you. Okay. And so you can convince yourself that if you just flip this upside down, you do not have the molecule on the right, or depending on the other molecule, it's mirror image. All right, because of the way that that chlorine, if I take this, so for example, I have this one. If I just take it and flip it, I do not have its mirror image. The chlorine is pointed in the wrong direction here, right? So these are distinct molecules. You built one of the two, but not both of them, right? They are 2 distinct molecules here.
So like so you can't rotate them anymore. They can be the same, just not exactly.
They are mirror images. You'd have to pick up and swap those 2 atoms in order to get the other molecule, right? You'd have to start making or breaking bonds in order to get your other molecule, okay? And this has everything to do with the tetrahedral geometry of these sp3 hybridized carbons. When we had rings, we had this cis-trans business because they were locked on certain sides. With tetrahedrals, we have this opportunity for these mirror images. What's up?
Okay, so the wedge bonds are the ones that are going into the page, is that right?
No, the dashes go into the page, the wedges stick out of the page.
Oh, okay.
Okay, so before we sort of move on in terms of how to spot these, let's make sure that we can draw mirror images here. So I'm going to put down a molecule, and you're going to draw me the mirror image. All right, so this first bond I have pointed up and to the right, so now it's got to go up and to the left on my mirror image. Keep going, put it on my, what do we got? 1, 2, 3, 4, 5, 6 carbons. Okay. All right, so this is how we can get our pair of enantiomers by putting in our little magic mirror and drawing the mirror image of that structure. Okay, there's another way that we could do this, and we want to be able to spy these pairs of enantiomers, so we're going to learn both. You're going to be asked to do both. And this is what we're going to call the dash to wedge method. Okay? So we had said that this is a pair of enantiomers here, right? So what if I pick up this molecule right here, the one on my right, and I rotate it 180 degrees? Right, so now I'm back to my similar carbon layout that I had over here on the left. My chlorine is on that third carbon, but now it's going to be pointed in to the board. Okay? So another way that we could take these molecules and draw its enantiomer is if we just copy-pasted exactly as it appears originally and turn any wedged bonds into dashes and any dashed bonds into wedges. Okay, this is also a pair of enantiomers. And to be clear, you can sort of, and this is where your model kits are really helpful, you can build it and convince yourself that this molecule here is exactly what you drew when you drew me the mirror image above. This is just two different methods of drawing the mirror image of a molecule. One to like literally just put a mirror in and draw its mirror image, or we can turn any wedges into dashes and dashes into wedges. Okay, both of those would give you your mirror images, your pair of enantiomers. So for our dash to wedge model, we're going to turn all dashes to wedges and all wedges to dashes. All right, so then one more here just to practice. Okay, draw me the enantiomer of this molecule right here using that dash to wedge method. All right, so I'm just going to copy paste exactly as it appeared, but I'm going to make this wedged bond right here into dashes. Now I have my pair of enantiomers. Okay, and if instead you had taken this molecule and drawn its enantiomer using the mirror image method, to be clear, these are the same molecule. All right, we have two different methods of getting to that same molecule. One is to take the mirror image, right? Imagine a mirror is there, draw its mirror image. The other one is to turn all wedges into dashes, okay? And if you sort of are having trouble seeing how they're the same, imagine that you had a spatula and you picked up this molecule and flipped it over like a pancake, okay? That's how you would sort of convert between those two. And again, if you build it with your model kit, it's much easier to see. Like I said, this was a chapter where I really relied heavily on my model kit. Okay, so again, we have two methods for being able to draw pairs of enantiomers. All right, and up until now, you just sort of trusted me that these were that they were chiral molecules, that they had these enantiomers, right? So how did I spy that? In your little in your little models that you just built here, there's one very key to why this molecule is a chiral molecule, and that is that carbon right there has 4 distinct bonds. It is bound to 4 different things. This chiral carbon right here is bound to a hydrogen, to a chlorine. On this side, it's 2 carbons long, and on this side is only 1 carbon long. So this carbon right here has 4 distinct bonds, which is what makes it a chiral carbon. Okay? So this terminology, give me one second. This terminology, chiral, a chiral carbon has 4 distinct bonds. Okay? Going back to this original example here, this carbon is a chiral carbon because on one side it's got an ethyl group, The other side is only 1 carbon long, so it's a methyl group. It's got this chlorine here, which we don't know how to name yet, but we call it a chloro group. And then implied, sticking in the back, is that hydrogen. All right, 4 distinct bonds. What's up?
Can you go back to that bromine example?
Sure. So this, I drew my pair of enantiomers by converting my wedged, or my dashed bond into a wedged bond.
Okay, I see it now.
And then the fluorine is the same, so it has the one kind of link to it.
Because, right, this is 3 carbons long, 1 carbon, a fluorine, and your implied hydrogen. 4 distinct bonds on that carbon. Okay? So, I'm going to put down some molecules, and let's see if we can spy the chiral carbons in these molecules. All right, try to identify the chiral carbons in these molecules. All right, so for this first one here, how many chiral centers does it have? It's got 1. This carbon right here. Right, and what are its 4 bonds? Let's go ahead and see. Notice that they're all, that carbon's bound to 3 other carbons, right? But they're still different groups because they're different sizes. This is 3 carbons long on this carbon right here, what we would call a propyl group. It's only 2 carbons long over here, what we would call an ethyl group. And over here it's 1 carbon long, what we would call a methyl group. And what is that 4th bond? Hydrogen, the implied hydrogen, right? Sticking back here. Okay? So you're not just looking at the atom it's bound to. You got to look at everything, right? How long is that carbon chain and compare? How many chiral centers do we have in the second molecule? Now we have 2. This carbon right here, you know, we can sort of list them off. It's bound to a chlorine, a methyl. I guess we can't really list it because we don't have a name for this thing here. This CHF-CH3, and a hydrogen. This is also a chiral center here. We got a fluorine, a methyl, that whole thing. CHCl, CH3, and then finally a hydrogen. All right, so this would be a molecule with 2 chiral centers. Take a second and draw me the enantiomer of this molecule. Pick whichever method you want. Okay, so I'm gonna do the wedge to dash method. I just want to be clear here. I would have to change both this dash to a wedge bond, and I would have to change this wedge to a dashed bond. All right, this would be my pair of enantiomers. All right, and then our last example here, how many chiral carbons does this molecule have? Boom, nice, excellent. Trick question, kind of. There are no chiral carbons in this particular molecule. So why is that? It's really tempting to say, well, this one right here, right? Because it's at the base of a wedge, and that's been the answer every time, okay? But this carbon is not bound to 4 distinct groups. 2 of those groups are identical. It's got a methyl group on this side and a methyl group on this side, right? It has to be 4 distinct groups in order for this carbon to be chiral. So since this is a CH3 and this is a CH3, this carbon right here is not chiral. We have a fancy word for that, achiral. That means not chiral. Chiral versus achiral. Achiral means it's not chiral. Yeah, I don't make the rules. Latin something or other, I'm sure. Okay. So, because it's really a consequence of the tetrahedral geometry of these carbons, the most common, or one common way and the easiest way to sort of analyze the chirality of a molecule is using this sort of stick figure here, which really sort of aims to show the tetrahedral geometry of a carbon atom. So let's go ahead and build this tetrahedral here. And this sort of skeletal structure here, we're going to fill in these bonds. But the whole point of this little stick figure here is to illustrate the tetrahedral geometry of a carbon atom. Right? You see all 4 bonds, and they're spaced out how they would be in space around that tetrahedral carbon. All right, so we're going to build a tetrahedral carbon, and we're going to use all different colors here. So grab a green, a white, a purple, and a yellow, or orange, I guess they are. Make sure we have a chiral carbon. We need 4 distinct bonds. Okay, so now take a second and build the mirror image of your molecule. All right, so we got both pairs of enantiomers. Right? Put them next to each other. They should be the mirror image of one another. All right, so first of all, convince yourself, take a second and convince yourself that because they are 4 distinct bonds, and they are mirror images of one another, you cannot superimpose these. There's no way to line it up so that all your bonds, you can get 2 out of 3, but then the other 2 are all messed up, right? That's because they are distinct molecules. They are a pair of stereoisomers, a pair of enantiomers. Okay, so now we're going to draw one of them into our little chair structure here. And I want that hydrogen to be on the back carbon. Right? So I'm going to pick this one here. My hydrogen is in the back. So that means I need to put my purple, which is my iodine, on top. My bromine over here, and my chlorine over here. Right, so this molecule right here is represented in that stick figure of a tetrahedral on the screen. Okay, so first, now let's draw the mirror image of this molecule. All right, but we're going to keep the framework of our tetrahedral the same. So let's just note, if we look at our mirror image over here, if I keep my hydrogen in the back, I'll keep my iodine on top. My chlorine and my bromine have switched places. So in our tetrahedral, structure, to get a pair of enantiomers, you're going to swap any 2 bonds. Any 2 that you would have swapped, you would have gotten your pair of enantiomers. Okay, in my case, I swapped my chlorine and my bromine. You could have picked any 2. Now, the whole point, just like we saw with our stereoisomers for our rings, is we have to build these into the names, the differences between these two stereoisomers. That's that R and that S designation. So how do I assign my R and my S stereoisomers? First thing we got to do is we got to look at all these groups and we got to assign them priority. Okay? So the hydrogen, the chlorine, the iodine, the bromine, I'm going to assign priority to these groups. All right, so what the heck does that mean? All right, so the higher the priority, the higher the atomic number. All right, and we're going to build on this set of rules here, but this one right away, we can assign priority to this particular molecule. All right, what's my highest priority group up here? Which is the highest, which element up there has the highest atomic number? Iodine. So iodine gets priority 1. What's next? The bromine's next, and chlorine after that. Hydrogen, being element 1, is going to be your lowest priority group. All right, so that's all the way now priority 4. Okay? So we got to go in for each of these groups and assign priority. Then we're going to rotate our molecule. So that the lowest priority group is pointing into the page. All right, in this case here, we'll do an example where we have to rotate it ourselves, but in this example here, my lowest priority group is already pointed into the page. Remember, that's what that wedged bond means. So we can say pointed into the page, meaning it's on, I'm sorry, not the wedge, the dashed bond. All right, and now we're going to draw in arrows connecting 1 to 2 to 3. So what do I mean by that? I'm going to draw an arrow from the group that's priority 1 to the group that's priority 2, from 2 to 3, and then 3 back to 1. Okay? If my arrows are pointed clockwise, that is the R stereoisomer. Counterclockwise is the S stereoisomer. All right, so first things first, I had to go in and assign priority to each of these groups. I'm going to orient my molecule in such a way that the lowest priority group is pointed into the page. I'm then going to draw arrows from 1 to 2, 2 to 3, and then 3 back to 1. And I'm going to look, are these pointed clockwise or counterclockwise? In this case, these would be counterclockwise. So this would be what we would call the S isomer. And if we look at its mirror image here, again, I'm going to go in and assign priority. Iodine's 1, bromine's 2, chlorine's 3, hydrogen's 4. If I look at its stereoisomer, or its enantiomer, now my arrows are all pointed clockwise, so this would be the R isomer. All right. So let's do one more. I want you guys to tell me which isomer this is all on your own here. So we're going to do a new molecule. All right, so what is my highest priority group in this molecule? The chlorine, that's got the highest atomic number. What would come next? Yeah, so I'm looking at oxygen versus carbon versus hydrogen. Which one has the higher atomic number? That would be oxygen, and then carbon, hydrogen in the back, right? Hydrogen's last. So now I'm going to draw my arrows connecting 1 to 2, 2 to 3, and 3 back to 1. This would be in the counterclockwise direction. So this is the S stereoisomer. You're looking at just the atom for right now. We'll talk about what happens if there's a tie here in a second. But yes, you're just looking at the atom that's bound to that chiral carbon and ranking them by their atomic number. All right, so now let's look at another example here. right, so now we have a bit of a different situation here when we're assigning priority. The highest priority group is easy. The lowest priority group is easy. But if I look at these two other groups, I'm comparing this carbon here with this carbon here, both of which have the same atomic number. They're both carbons, right? So now we have this like tie breaking that we have to have, where what we're going to do is we're going to list everything that's bound to each of those carbons. So this carbon that I colored in orange here is bound to 3 hydrogens. This carbon that I colored in blue has 2 hydrogens, but then is bound to another carbon, to this one right here. So if I look at these lists, hydrogens tie, but now all of a sudden I have this tiebreaker here because this one is bound to a carbon and this one is just bound to 3 hydrogens. Okay, so when we're assigning a priority, highest atomic number, if there's a tie, we have to list everything bound to that atom and look for the largest atomic number. Okay. If it's a double bond, you want to list that atom twice. I'll show you what I mean by that here in a second. Okay, so going back here to this example, because this, and this is going to be the case, like if the longer the chain is, the higher the priority, right? Because it's going to be bound to more carbons. So this would get priority 2, and this carbon is priority 3. So then take a second and tell me whether we were looking at the R or the S stereoisomer. One to 2, 2 to 3, 3 back to 1, all in the clockwise direction, and clockwise is R. To the list.
Yeah, thank you. The list is that far up.
All right, so now all these examples here, I had drawn them with the hydrogen pointed in the back, which we need in order to assign our chirality. So what are we supposed to do if we get to a molecule like this? And we go back to our other one here. Okay, so now yes. All right, so now I can't assign chirality yet because my hydrogen, my lowest priority group has to be pointed into the page. So what am I supposed to do if I come to an example like this? We need to rotate this molecule so that that lowest priority group is in the page, okay? So if I was using my model kit, how would I do it? How would I rotate this so that so that my hydrogen is pointed towards me? I would just pick it up and spin it, okay? So that's exactly what we're going to do. Notice that my top bond stays the same. I'm just spinning and rotating those bottom 3 bonds. So in order to get my hydrogen into the right position, I need to rotate this molecule here. Okay? My iodine is going to stay in the exact same place. And all of my other 3 bonds are going to swap places here. So my hydrogen is going to go where the chlorine was. The chlorine is going to go where the bromine was. And the bromine's going to go where the hydrogen was, right? So I have to rotate to put that lowest priority group into the right position. And now I can assign my priority. 1, 2, 3. This was going in the counterclockwise direction. So this was that S isomer. All right, so I'm going to put down a bunch more examples here, and I want you all to determine whether they are the R or the S stereoisomer.
So we can put a little C on it, since we're pressing. So C is right down here, so we're just gonna leave that alone, that's the tie.
This is a carbon and this is a carbon, so that's the tie.
So now we're just comparing all of the H's.
Well, so this carbon right here is bound to 2 hydrogens and 1 carbon,
Oh.
and this one's only bound to 3 hydrogens.
Oh, okay,
So that's why we list them all out, and whichever has the highest atomic number in our list here is going to be the one that gets the higher priority.
Okay, so we'll need to go just one more over, not the whole to the end of it.
Correct.
Okay.
Yeah, if there was a tie here, then you would keep on moving down the line.
Okay, got it.
All right, so for this one here, let's just split this up. I can't assign stuff just yet because it isn't oriented correctly, right? Or I guess I can assign, but I need that fourth priority group in the back, right? So what we're gonna do to rotate this into position is keep one of these bonds in the same position, right? So I'm just gonna keep that C double bonded to the oxygen in the same place. And I'm going to swap, since I want hydrogen in the back, I'm going to rotate this like this. All three of those groups have to change positions. So now my hydrogen's here, my methyl group's here, and my chlorine is here. Okay? We got hydrogen as our low priority group. What's our highest priority group? The chlorine. Now here I have a carbon tied with a carbon. So we're going to list everything that they're bound to. And since this is double bonded to an oxygen, I'm going to put that on my list twice. This methyl group is just 3 hydrogens. So comparing this list to this list, which one is it going to be? The top one, A or B? A. That's going to be my highest, or my next highest priority group. And the methyl will be 3. All right, so 1 to 2, 2 to 3, 3 back to 1. This would be counterclockwise, so this is, yes, this is my S isomer here. Okay. All right, so here, again, my hydrogen is in the wrong place. All right, so again, I'm going to have to rotate it into the correct position. Now it's on top, but we're still going to play the same game, right? Just like you would if you were in this predicament here. You would grab one of those bonds and spin it, right? So when we rotate these molecules, we always keep one bond the same and move the other 3. So I'm going to go ahead and keep that ethyl group where it is. I'm going to move hydrogen over here. Boom, boom. Swap all that. Okay, my highest priority is definitely that iodine. When I'm comparing my methyl group to my ethyl group, which one is going to be higher priority? The ethyl group, right? Because this carbon is bound to 2 hydrogens and another carbon, whereas this one's just bound to 3 hydrogens. So you're 2, you're 3. So this would be the R stereoisomer. These groups are clockwise to one another. All right, so let's just practice this a bunch more. I want everybody to take a second and build me using your model kits the following molecule. This would be if it was on a dash. So you swap your chlorine and your hydrogen. The chlorine should be pointed at you. Yep, that's good. Okay, and then I want, using your model kits, I want you to pick this thing up and spin it around so that it's in the proper orientation and assign this the R or S chirality, right? You need to look at it in such a way that your hydrogen is pointing into the page, pointing into the table, I guess. So which one do we have, R or S? What do we think? So let's see, show of hands. Who thinks we have the S molecule? Who thinks we have the R molecule? So this would be the S, okay? I'm going to draw this now into that tetrahedral, right? So that would be if I put it down like that with the hydrogen in the back, okay? All right, I got to draw it with the hydrogen in the back. All right. So this molecule here, we're going to convert it into this tetrahedral-y thingy that we're used to looking at, where my hydrogen is in the back, my chlorine's over here. This would just be that methyl group. And then this is a whole bunch, CH2, CH2, CH3, a propyl group. All right, if we're assigning priority, chlorine is the highest. That propyl group comes next, followed by my methyl group. And so these are all in the counterclockwise or S stereoisomer. Yeah. All right, let's do another one. Okay, you can do this one. First, actually, you're going to tell me how many chiral carbons it has. And then we want the stereochemistry, either R or S, on each chiral carbon. Okay, and using your model kits, you're going to tell me whether we have the R or the S configuration here. Okay, so this one has how many chiral centers? 2. This one and this one. Okay. They are 2 carbons, but this one has a bromine on it, so these are not identical. All right, and so if you have 2 chiral centers, then each one is going to have its own label of R or S. All right, and so next class we will learn how to assign priority based on our normal sort of looking structures here. We were dealing specifically with those tetrahedral structures, okay, but we should still be able to do it with our model kit here. I'm going to grab my molecule and make sure to hold it with that hydrogen pointed away, pointed into the board. What's going to be my highest priority group on this carbon right here? We can go ahead and assign priority still. On this carbon, what's the highest priority group? The bromine. And then which side is higher priority, the left or the right? The left. So this is 2 and this is 3, okay? I can't do it based on this picture though because my hydrogen's now pointed in the right direction. But if I look at my model kit, bromine's 1, this big ugly thing is 2, my methyl group's 3, so that would be the clockwise direction. Okay, so we can see that this would be the R stereochemistry for that particular carbon. I'm just going to redraw my picture. We'll look at the other carbon. Okay, looking at my middle carbon now. I'll tell you, our methyl group is going to be priority 3. Which one, let's say, this fragment right here we're going to call A. This one over here we're going to call B. Which one's higher priority, A or B? B. So they're both carbons, right? I'm going to compare this carbon and this carbon. But now I have to list everything it's bound to. This is bound to 2 hydrogens and a carbon. This is bound to hydrogen, a carbon, and a bromine. So this is the higher priority group. 1, 2, 3. Okay, again, if I'm looking at my model kit, I'm going to turn this in such a way that my hydrogen on that carbon is pointed into the page. So that'd be 1, 2, 3. Again, this is clockwise, so this is also an R stereocenter.
I didn't get that. Could you try?
He's fine. Okay. All right. So we'll sort of learn how to do this. So we learned with our model kits. We learned using those tetrahedral structures. Those are kind of special structures, though, right? We're not really used to looking at molecules that way. So next class, we'll come in and we'll look at just these sort of skeletal structures here. How do we assign R and S? And then finally, how do we put it all together into the name of a molecule? All right, and again, this particular chapter, model kits are a lifesaver. We have them, obviously we have them here in this room. If you come in and grasp, you can rent one, you can check one out to use for your homework as well. You do not have your own. Say it again? I don't know.
I have one that I just
Online?
sign up right now, yeah.
Oh, cool.
Maybe you can put the red one.
Is it free?
Yeah.
Is it just a website? Cool.
I'm just trying to make sure that you can make your
It seems like there should be at this
Yeah,
point, but I don't know what it
it's
is.